Hi, everyone. So today we're going to start related rates. And related rates, if you've got a function, let's say, for example, area equals pi r squared. Normally when we take the derivative of both sides, oops, normally when we take the derivative of both sides, it's with respect to this independent variable over here. And so we'd end up with dA dr equals 2 pi r. Well, that's not what we're going to be doing here. We're going to be relating these things to some other variable. So I'm still going to be starting off with area equals pi r squared, but now I'm going to be taking the derivative, say, with respect to time. Not always, but often. So on the left-hand side, I'm going to have dA dt. And on the right-hand side, look, we're not taking the derivative with respect to r, we're taking it with respect to t. So we're going to have 2 pi r, because we took the derivative of the outside function, and now we're going to go back and take the derivative of the inside function with respect to time. So times dr dt. Notice, dA dt is a rate. It's the rate of change in area with respect to time. And dr dt is the rate of change in radius with respect to time. We're relating this rate of change and this rate of change. That's why these are called related rates problems. So I want to take a look at this first worksheet with you. And if all goes well, you brought it home with you tonight to watch this with. Problem number 1, this is 73 in class. Problem number 1, when a circular plate of metal is heated in an oven, the radius increases at a rate of 0.001 centimeters per second. Now, let's think about this. I think one thing, if I had a piece of advice to give you, it's name things calculously. So when I look at the words in front of this number, the words are its radius increases at a rate of 0.001 centimeters per second. So I'm going to name this number dr dt. It's a change in radius with respect to time. Okay? So name things calculously. Next, at what rate is the plate's area increasing? At what rate is the plate's area increasing? Well, let's think about naming this calculously. Area is increasing. What rate? Oh, well, that's going to be dA dt. They're asking about dA dt. They've given me dr dt equals 0.001 centimeters per second. And they'd like to know dA dt. They've told me that this is a circular plate. So do we have a relationship between area and radius for this shape? Sure. Area equals pi r squared. This is the relationship I need to bring to the problem so that when I take the derivative of both sides with respect to time, I'll get a dA dt on the left and a dr dt on the right. Okay, so, oh, and there's one other given piece of information. Not only is dr dt 0.001 centimeters per second, radius is 50. Now, this is not a constant. The radius is not always 50. And because the radius is changing, and we know the radius is changing because there's a dr dt, it tells me the radius is changing, I can't plug constants in now. Don't plug this constant in until, don't plug this not constant in until after you've taken the derivative. The only thing that can be plugged in before you take the derivative is a constant. Okay, so I'm going to take the derivative of both sides with respect to time. I'm going to, on the left-hand side, get dA dt. Oh, that's the thing they asked me for. On the right-hand side, when I take the derivative of pi r squared, I get 2 pi r times the derivative of the inside r function with respect to time, dr dt. Now let's plug in what we know. We know radius is 50, and we know dr dt is 0.001. And think about the units here. This is centimeters. This is centimeters per second. So we're going to end up with 0.1 pi centimeters times centimeters is centimeters squared per second. Well, isn't centimeters squared per second a change in area with respect to a change in time? So there's my dA dt. dA dt is this. Okay. In fact, I'm just going to pick up a calculator and check that just to make sure. I multiplied 100 times 0.001. Yes, 0.1. Okay. Question 2. A hot air balloon straight up from a level field is tracked by a rangefinder. Here's the balloon. Here's the rangefinder, 500 meters from the balloon's liftoff point. There's where the balloon lifted off. At the moment, the rangefinder's angle of elevation, but look, that's not a constant. This is changing. As the balloon goes higher and higher, that angle, which was down here, and then here, and then here, that angle gets bigger and bigger. So I'm not going to be plugging pi over, I'm not going to be plugging pi over 4 in here until after I take the derivative. Though, look and notice 500 is a constant. The rangefinder isn't getting closer and further back, so I can plug that value in right away. Okay. The angle is changing. At 0.114 radians per minute. Well, what is that? What would that be if we named it calculusly? It's a change in angle with respect to time. So I'm going to say that d theta dt equals 0.114 radians per minute, and theta equals pi over 4. Okay, these are both changing quantities, so there's no plugging them in now. How fast is the balloon rising at that moment? Well, here's the height of the balloon. What are they asking about if they're talking about how fast is the balloon rising? How fast is the balloon rising? Well, they want to know at what rate is the height changing with respect to time. So they're asking, what's dH dt? So I'm looking for a way to relate theta and h. Do we know a relationship between theta and h that we could use here? Well, theta is an angle, h is the opposite side, 500 is the adjacent side. It sounds like tangent is going to be what I need. I'm going to say tangent of theta equals h over 500. Or 1 over 500 h equals tangent theta. Now I'm going to take the derivative of both sides with respect to time because I want to know how fast is this height changing with respect to time. On the left-hand side, I'm going to have secant squared theta d theta dt. On the right-hand side, I've got 1 over 500, the derivative of h with respect to time, dh dt. Well, this is the thing I'm looking for. This they gave me. This is 0.114. And secant of theta. Well, let's think about the secant of theta. We've got this situation here where this is pi over 4 and pi over 4. And we know that this is 500. So because of our geometry knowledge and our trig knowledge, we know that this would also be 500, and this would be 500 root 2. Now, we're looking at secant squared theta. So let's start with cosine theta. Cosine theta from our picture would be 500 over 500 root 2. Oh, but we knew that, didn't we? We knew it was going to be root 2 over 2 because the cosine of pi over 4 is root 2 over 2. But remember, we're looking for secant squared. So if cosine is 1 over root 2, then secant is root 2 over 1. And therefore, secant squared is going to be 2. So remember what we had. We had secant squared theta d theta dt equals 1 over 500 dh dt. Well, if I multiply both sides by 500, I'll get dh dt alone. And that'll be, we said secant squared was 2. We said d theta dt was 0.114. And we multiplied both sides by 500. And so I end up with 114 meters per minute is dh dt. Okay. Does that make sense in the context of this problem? We had to come up with an equation to relate these things. And that was our tangent equation. What told me to use tangent? Well, when I thought about what I had and what I was looking for, I wanted to know dh dt. They gave me d theta dt. I said to myself, do I know a relationship for this related rates problem between theta and h? And the relationship between theta and h, given that we know 500, is tangent. So I'm going to have to name things calculously to help me figure out the relationship that I need to bring to the problem so that I can take the derivative of that relationship and plug in the stuff I know. Okay, question 3. The radius and surface area of a sphere are related by s equals 4 pi r squared. Write an equation that relates ds dt to dr dt. Oh, well, that's pretty straightforward. They just want me to take the derivative with respect to time of both sides. On the left-hand side, I've got ds dt. On the right-hand side, I take the derivative of 4 pi r squared and get 8 pi r times the derivative of the inside r function with respect to time, dr dt. That's it. I don't have to do anything more for question 3. Don't forget to write sentences. There's no justifying in related rates, though. Phew. Okay. 4. The radius r, height h, and volume v of a right circular cylinder are related by, so there's our radius, there's our height, volume equals pi r squared h. Remember, you're expected to know these formulas, so if you don't, please write them down on that page of formulas in your notebook and study the heck out of them for our next test on December 7th. Okay, how is dv dt related to dh dt if r is a constant? Okay, so we're looking at r as a constant now, like 3. We have a fixed radius. It's never changing. Well, if the radius is a constant, and I'm going to take the derivative of both sides, v equals pi r squared h. If I'm going to take the derivative of both sides with respect to time, remember, because they said they wanted dv dt, and they wanted to know how that was related to dh dt, well, all this here is constant. So the derivative of a constant times h with respect to time is going to be that constant times the derivative of h with respect to time. That's dv dt. Now, in part B, we're told that height is a constant, and we're asked to approach the same problem again. Pi r squared height. This time, height is a constant, and so I might want to write this as pi h times r squared, a constant times a function. This is what I want to take the derivative of with respect to time. And so on the left-hand side, no problem, dv dt. But on the right-hand side, I have a constant times the derivative of r squared. Well, the derivative of r squared is 2r times the derivative of the inside r function with respect to time, times dr dt. So 2 pi r h dr dt. And by the way, that's the area, the lateral area of the cylinder. 2 pi r h is this area. It's everything except the circular top and bottom. Okay, let's take a look at part C now. Part C is the more engaging, more challenging part where we're told neither r nor h is constant. So when I look at v equals pi r squared under these conditions, these are both variables, and they're connected with multiplication. So this becomes a product rule problem. So dv dt equals pi r squared times the derivative of this with respect to time, dh dt, plus this pi h times the derivative of r squared, 2 pi r, 2r dr dt, 2r dr dt. Now you can see we have a lot more stuff that we would need to plug in for here, right? We're going to be looking for one thing, but how many unknowns are there? There's dr dt, there's r, there's h, there's dh dt, and there's dv dt. So they're going to have to give me 4 of those 5 pieces of information in order to solve a problem like this. The problems are much easier, like in A and B, where one of those values, either height or radius, is held as a constant. But sometimes both of them are changing. And as a result, we end up with some relationship like this. Okay, but this isn't a problem where we go any further. They just want to know a relationship between dv dt and dh dt and dr dt. And that's what we've got here. Remember, I saw a product here. Now, we didn't have a product before in part A. Why not? Because when we were looking at part A and part B, we were told that in this case, height was a constant. And if height is a constant, it's a number. So no, the derivative of that number would be 0, and that part of that product rule would go away. I think it's much easier to think about this not in terms of product rule for this kind of a problem, but as the derivative of a constant times a function. When I have the derivative of a constant times a function, the derivative is that constant times the derivative of the function. That's what I'm using when I do parts A and part B. But when I get to part C, here, I definitely have to use the product rule. Okay, question 5. A spherical balloon is inflated by pumping air in at a rate of 10 cubic centimeters per second. Now, look at that and tell me what it is. What are those units? Are those the units of area? Are those the units of radius? No, those are the units of volume, and those are the units of time. So this is dV dt. I have to be able to name these things calculously. This thing's calculus name is dV dt. Okay, they've given me dV dt. Now what? How fast is the radius changing? How fast is radius changing when r equals 5 centimeters? Well, how fast is radius changing? What is that calculously? It's a change in radius with respect to time. So this is dr dt equals what? How fast is radius changing when r equals 5? Is r constant? No, radius is changing in this problem. So you're not going to be plugging this 5 in right away. You can only plug this 5 in after you take the derivative. But the derivative of what? Well, they told me here that dV dt was equal to 10. And they asked me about dr dt. Do we know a relationship between volume and radius for a sphere? Because we're told this is a spherical balloon. Sure. Volume equals 4/3 pi r cubed. Yeah, that's another formula you're supposed to know. So when I take the derivative of both sides here with respect to time, on the left-hand side, I've got dV dt. On the right-hand side, I have 4 pi r squared. Don't forget chain rule. You need to come back and take the derivative of that inside function with respect to time. So times dr dt. Okay, remember, they told me dV dt was 10. They told me that the radius was 5. dr dt. Now, let's even think about this from a units perspective. These are centimeters cubed per second. Here we have centimeters being squared. So I'm going to have 100 pi centimeters squared times dr dt equals 10 centimeters cubed per second. Well, if I now divide both sides by 100 pi centimeters squared, 100 pi centimeters squared, I can see that centimeters squared and these centimeters will cancel. This 10 will cancel here, and I'll end up with 1 over 10 pi for numbers, but look at the units. Centimeters on top, seconds on the bottom. And that's a change in radius over a change in time. dr dt equals 1 over 10 pi centimeters per second. Okay, so again, what are we doing here? Well, all we're doing is taking this equation, well, I guess we're starting even before that. We're translating the words and numbers into some calculus thoughts. dV dt is 10. What's dr dt when r is 5? Then we say to ourselves, all right, do we know a relationship between volume and radius here? And we sure do. We know that volume equals 4/3 pi r cubed. We take the derivative of both sides with respect to time. We end up with this equation, and then we can plug in the given radius, a changing quantity, and the given dV dt, 10 centimeters cubed per second, and use that to solve for dr dt. So in some ways, I think these problems are easier than optimization problems, especially if I can identify the relationship or equation that connects the two variables. Okay, 6. We've got a cone problem. Cone problems are very common in related rates land. We've got a radius and we've got a height. Now we know that the height of this whole cone is 10 meters. And we know that the radius up here is 5 meters. Whew. And we've also got how full is our cone of sand? No, water. Water is pumped into a cone-shaped tank at a rate of 9 meters cubed per minute. Well, how would we name that calculously? Meters cubed? Is that a change in surface area? Is that a change in radius? What is that? Meters cubed is volume. So I'm looking at dV/dt here. And what are they asking me about? They said, how fast is the water level rising the instant the water is 6 meters deep? How fast is the water level rising? They want to know dH/dt when h equals 6. Okay, so do I know a relationship between volume and height for this shape? Well, sure. This is a cone. I know volume of a cone. And if you don't, you should write it down now. 1/3 pi r squared h. Uh-oh. Well, wait a minute. I have this other variable, and I don't know dr/dt. I really don't want to take the derivative of this until this volume equation is only in terms of height. If you try and take the derivative now with product rule, you're going to have to come up with a dr/dt, and we don't have a dr/dt in this problem. So I think we need a helping equation, something that will let us get rid of this r squared and replace it with some he stuff. Well, let's see what we can think of when we go back to this picture for a moment. Who remembers from geometry similar triangles? Look at that. R is to H as 5 is to 10. See, this is the little triangle, radius, height, and these are from the big triangle. Radius is a constant 5, height is a constant 10. So I have this helping equation over here. And what was it we were trying to get rid of? We were trying to get rid of r. So solve this equation for r by multiplying both sides by h. You get r equals 1/2 h. Aha! Now I know what r is in terms of h. I can come back down here and replace r with 1/2 h. In cone problems, you often use, and in shadow problems, you often use similar triangles. So don't think that was a fluke. That's going to be very common for us. Okay, so what do we know? We know v equals 1/3. In fact, I'm going to write it as pi over 3, 1/2 h squared times h. Now, please make sure when you square the h, you also square the 1/2. So that's going to give me volume equals pi over 3, h squared over 4 times h. Or volume equals pi over 12, h to the 3rd. There's volume of the cone written only in terms of height. Now when I take the derivative of both sides with respect to time, on the left-hand side, I get dV/dt. On the right-hand side, I'm going to get the constant times the derivative of h to the 3rd, which is 3h squared. Don't forget chain rule and take the derivative of that inside h function with respect to t. All right, we've got a lot of information here now. Remember, they said, how fast is the water level rising? Water is being pumped in at 9 cubic meters per minute. And over here, the 3 and the 12 will cancel. I'll have pi over 4 when h is 6 meters. So when I get to this point, things should be pretty straightforward. 9 equals 36 pi over 4 dH dt. Or when I simplify here, I get 9 equals 9 pi dH dt. I'll divide both sides by 9 pi. Please don't migrate the pi to the top. My answer is 1 over pi dH dt. And yes, it is the end of 7th period, which means it's 4:35. And I need units on dH dt. What were my units here? Well, if I go back and see, height is measured in meters, radius is measured in meters, time is measured in minutes, and so I need then meters per minute. And what does this mean? It means the height is changing at a rate of 1 meter every pi minutes, or 1 over pi meters per minute. I like reading it as 1 meter every pi minutes. That makes a lot of sense to me visually, but 1 over pi meters per minute is certainly another accurate way of understanding this rate. Okay, again, what did we do here? We started by naming things calculously. They told me the water was being pumped in at 10 meters cubed per minute. So I knew that was a change in volume with respect to time, therefore dV dt. And they said, how fast is the water level rising? They wanted to know the change in the height with respect to time, or dH dt, when h was equal to 6. Now, here, it was no problem for me to come up with a relationship between them, but I got scared when I saw, uh-oh, this volume is in terms of two different variables. And I really didn't want to take the derivative until I had volume in terms of one variable. I needed a helping equation, and that helping equation came from similar triangles. Short side in the small triangle is to long leg in the small triangle. Short side in the big triangle is to long leg in the big triangle. Short to long, short to long. That's what I did when I created this relationship here. Which do I solve for? You solve for the one you want to get rid of. That's the one you need to solve for. Okay, so we solved for r. We plugged r into this other equation. Don't forget we had to square 1/2 h, squaring the h and squaring the 1/2. And that allowed me to simplify to pi over 12h to the third. Now the calculus, pretty straightforward. We took the derivative with respect to time of both sides, and then we plugged in our h, we plugged in our dV dt, and we solved for dH dt. I think the calculus in these problems is pretty easy, certainly easier than in the optimization problems. Okay, back of the worksheet, number 7. A road and a railroad track cross at right angles. You're going to see a lot of intersection problems like this, whether it's a road and a railroad track, or maybe it's a ladder leaning up against a building. You're going to see all kinds of intersection problems. And one thing that's true for every single intersection problem is when we're heading towards the intersection, rates are negative. And when we're heading away from the intersection, doesn't matter which direction, when we're headed away from the intersection, rates are positive. That's true for all intersection problems like numbers 7, 8, and 9. Okay, let's take a look at 7. 7 says we've got a road and a railroad track. at right angles. The train is heading south at 60 miles per hour. The train is zero point 0.6 miles north. So t equals zero point 0.6, and the train is moving at 60 miles an hour. That's dt. dt is 60 miles per hour. The car is moving east, and the car is already east of the intersection. Here's the car, and its distance is zero point 0.8, and the car is moving at dc dt. The car is moving at 20 miles per hour this way. The train is moving south. Uh-oh. Train is headed south. Don't forget, if the train is headed towards that intersection, that rate has to be negative. Okay, so what do I see here? How fast is the... Oh, I read that wrong. Did you see? It asks me how fast is the car moving. Oh, I don't know this amount. It says the distance between the two is changing at 20 miles an hour. The change in the distance, so this is the distance, and they're telling me that dt equals 20. Whoa, I've got a C, I've got a T, I've got a D. Luckily, I already see a relationship between these three variables, the Pythagorean theorem. So we know that C squared plus T squared equals D squared. And if I take the derivative with respect to time everywhere, I'm going to have 2c dc dt plus 2t dt dt equals 2d d dt. Now what do we know? Well, we know that c is 0.8. We don't know dc dt. That's the thing we're solving for. We know that t is 0.6 and headed at negative 60. And we know dt is 20. But what about d? How am I going to find d? Well, let's go back up to the picture and say, if this is 0.8 and this is 0.6, how can I find this? Well, I could always use the Pythagorean theorem. Hopefully you recognize that this was a 3, 4, 5 right triangle, or at least a multiple of a 3, 4, 5, and you ended up with d equal to 1 mile. Pythagorean triples show up in these problems a lot. Okay, so I'm going to plug in my 1 for d. d equals 1. Well, it looks like we've plugged in for everything, and we can now solve for dc dt. Yes, you notice back up here where when we took the derivative with respect to time, we had all these 2's. You can certainly divide everything by 2 and get rid of all those 2's. You don't need to make this problem more complicated. So I've got 0.8 dc dt equals, I guess I don't have equals yet. I have minus 36 equals 20. So I'm going to add 36 to both sides and get 0.8 dc dt equals 56. And 0.8 is the same as 8 tenths. So I'm going to get rid of 0.8 by multiplying both sides by 10 over 8. And so this will cancel with these. And here this will cancel with this, leaving me a 7. And so dc dt is 70. The car is moving at 70 miles per hour. Probably not a good thing if you're near an intersection with a train, but you know, under certain circumstances, that could be reasonable. Okay, so notice here we had to use Pythagorean theorem. Pythagorean theorem was the relationship between the distance for the train, the distance of the car, and the distance between the two objects. You will find a lot of Pythagorean theorem problems. Many of the intersection problems we do will be Pythagorean theorem problems. Okay, next. Convoy. Two convoys leave a depot. Here's the depot. Convoy A heads due east at 30 miles per hour. So we know that the change in A with respect to time is 30. Convoy B travels north at 40. dv dt equals 40. How fast is the distance between the convoys changing? d dt is what we're being asked to find. How fast is the distance changing? 6 minutes later, when convoy A equals 4 miles from the depot, and convoy B equals 3 miles from the depot. All right, do we know a relationship between A, B, and D? Sure, it's another Pythagorean theorem problem. So we know that A squared plus B squared equals D squared. And when we take the derivative of everything with respect to time, we'll get 2A dA dt plus 2B dB dt equals 2D d dt. And we can plug in what we know. We know A is 4 and dA dt is 30. 2 times 4 times 30. We know that B is 3 and dB dt is 40. We're looking for d dt. What about D? How can we find D? Well, I go back up here and I say this was 4 and this was 3, and I want to know about that. I could certainly use the Pythagorean theorem, or I could just recognize a 3, 4, 5 right triangle and say D equals 5. So we plug in D equal to 5 here, times d dt. And let me change that to big D. Not for any other reason than it's better, because it's what I wrote before. All right, so what do we have here? Ugh, I want to get rid of these 2's. So I'm going to have 120 plus 120 equals 5b d dt. So 240 over 5 equals d dt. 5 goes into 24 4 times, 8. And these units are miles per hour is d dt. Okay. So again, intersection problems are often, not always, but often Pythagorean theorem. Sometimes they're tricky. Sometimes they're area-y. Let's take a look at problem number 9. Problem 9, a 13-foot ladder. Does the ladder change its length? No. This is a 13-foot ladder. The ladder is a constant. I plug the 13 in at the beginning of the problem. Okay. 13-foot ladder. I'm going to call this X. I'm going to call this Y. The 13-foot ladder is leaning up against a house when the base starts to slide away from the bottom of the wall. Okay, so if the base is sliding away from the bottom of the wall, that means that the base is moving away from the intersection this way. And so we're talking about dx dt. What does it say about dx dt? The base is moving at 5 feet per second. 5 feet per second. The instant the base is 12 feet from the ladder is 12 feet from the base. So x equals 12 and dx dt is 5. Okay, what else do we know? Do we know anything else? 13-foot ladder? Oh, well, what about y? Oh yeah, Pythagorean theorem. 5, 12, 13. You could always use the Pythagorean theorem if you don't remember that. Um, A, how fast is the top of the ladder sliding down the wall at that instant? So we want to know about this. We want to know about dy dt. And since the top of the ladder is headed towards our intersection, we expect dy dt to be a negative number. Don't be surprised by that. Okay, so do we have a relationship here? Sure, it's still the Pythagorean theorem. This time, however, 13 is a constant, and I plug that in at the beginning of the problem. So I'm going to have x squared plus y squared equals 13 squared, or 169. Now, when I go to take the derivative over here, the derivative here will be 2x dx dt plus 2y dy dt. And I can't tell you how many people over here want to do 2 times 13 times 13. No, this is a number. 169 is a number. The derivative of a number is 0. You have to find the derivative of a constant to be 0. This is why it's terribly important to plug the constant in at the beginning. Because when I take the derivative of that constant, I need that 0 to show up. Okay, so what do we know? We know that x equals 12 and dx dt was 5. We know that y was 5, and we're looking for dy dt. So I get 24 times 5, or 120, plus 10 dy dt equals 0, or 10 dy dt equals negative 120, or dy dt equals negative 12 feet per second. That negative tells me that the ladder is sliding down the wall. If I had had a positive here, I would have thought the ladder was sliding up the wall away from the ground. Well, our ladder is sliding down the wall towards the intersection, and therefore dy dt is negative. Okay, part B. That was part A. Part B. This one's a little different. How fast is the area of the triangle formed? Area. How fast is the area of the triangle formed by the ladder, the ground, and the wall changing at that same instant? Well, remember, x was 12, and dx dt was equal to 5. We knew that y was equal to 5. We knew that the ladder was 13. And we know that dy dt, because we just solved for it, was negative 12. So what about the area of this shape? Well, area will be 1/2 x times y. Now, when I take the derivative here, I have two choices. I can use a helping equation like x squared plus y squared equals 169. But then when I solve for y, I've got this nasty thing to deal with. I don't want to plug this in here and then have to take the derivative of that. This is a situation where I would actually much prefer to have two variables present and to use the product rule. Why? Well, when I take the derivative of x with respect to time, I got dx dt, and they've given me that. And when I also take the derivative of y with respect to time, look, there's dy dt. I've also found that in part A. So I'm just going to take the derivative of 1/2 xy with the product rule. So I'm going to get dA dt equals 1/2. Now, x times dy dt plus y times dx dt. And what can we say here? Well, we know that x is equal to 12, dy dt is negative 12, and y was equal to 5, and dx dt was equal to 5. So I end up with 1/2 negative 144 plus 25, or negative 119 over 2 is dA dt. Now, what are my units here? My units here, the change in area will be feet squared, And time, we're still dealing with seconds. So the area is changing by 119 feet by getting smaller 119 square feet every 2 seconds, or negative 59.5 square feet per 1 second. Okay, so that's those 9. 10, I don't want to do. I'll set it up for you. Um, it's kind of like an intersection problem, except it's not. Two ships moving away from point O so that they're 120 miles apart, 120 degrees apart. Ship A moves at 14 knots, so dAdt is 14. Ship B moves at 21 knots. How far apart are they when A equals 5 and B equals 3? All right, so how far apart are they? Guess what? This isn't a right triangle. D. Um, so do you remember when you're given a side, and the angle in between, how you find that opposite side? Why, that's right. This is law of cosines. And the reason I don't want to do this problem is because it will utilize the law of cosines. All right, so what would it look like if I stopped whining and just did it? Well, okay, law of cosines, remember, says a squared plus b squared minus 2ab cosine c equals c squared. But in our problem, we've got a squared plus b squared minus 2ab cosine O equals d squared. Okay, so A was 5, so I have 25 plus B was 3 minus 2 times 5 times 3, or 10 times 3, 30. Cosine 120 equals d squared. Hey, this is just us finding d. We haven't even taken a derivative yet. All right, what's the cosine of 120? Well, the cosine of 120 is negative a half times negative 30, and over here we have 34 equals d squared. So I end up with 34 plus 15 is d squared, and so d equals, or d squared is 49, and so d equals 7. Whew. All right, so now we know d is 7. We did some tricky stuff. D equals 7. But remember, the question was, how fast is the distance between the two changing? They want to know d dt. Bah! Yes, I have to go and take the derivative of law of cosines. Okay, so I've got a squared plus b squared minus 2 times a times b cosine of this constant angle equals d squared. So over here we're going to have 2a dA dt plus 2b dB dt equals, well, look, we know the cosine of 120 is negative 1/2 times this negative 2 is positive 1. So I just now have to worry about the derivative of a times b, which is a times dB dt plus b times dA dt. And on the other side of the equation, we have 2d dd dt. And now we can plug in everything. We're looking for d dt. We know that a is 5. We know that dA dt is 14. We know that b is 3, and dB dt is 21, plus 5 times 21 plus 3 times 14 equals, what was d? 7. 2 times 7 is 14 times d dt. So we're almost there. Yeah, but I've run out of room on this board. 140, 6 times 21 is 126, 105, and 42 equals 14 dt. So this is 100, 200, 300, 340, 366, 371, 373, 413. 413 over 14 equals d dt in knots. These are knots, nautical miles per hour. Well, it's, yeah, ew, 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 I feel dirty. There's nothing this hard that we have to do until probably the 4th day of related rates. So don't worry about this. Instead, think about watching this video again, going through this worksheet problems again, and getting ready for tomorrow. In class tomorrow, you're going to be working on assignment number 73, the bookwork problems, and there are 7 of them with related rates. So good luck, bon chance, and I will see you on Friday. I look forward to taking your questions about related rates. Have a nice night, everyone.